Okay, in this video, we've got our last application of integration for the semester, and that's finding the area between two curves. So in the last section, we talked about finding the area under a curve to the x-axis. So this time we've got two different functions, and we're wanting to find the area of the bounded region between those two functions. And so basically what this definition says here is that you can find the area between two functions by taking the definite integral of the difference of the two functions, where those limits of integration are the endpoints or the interval that's bounded by those two functions. And I'll show you that here in this picture. So here we have an area shaded in blue that's created by drawing the parabola negative x squared plus 5 and the line x minus 1. So when you shade the region that's bounded by those two curves, you get that shaded region in blue. And we want to find that area of that blue region. So the first thing that I need to do is start by finding where my limits of integration are. So those will be the numbers that I put on my integral symbol. Now, the limits of integration in our previous section were usually given to us by some closed interval where we were looking. In these problems, you're going to have to determine what that closed interval is. And in the picture, that closed interval is going to be the leftmost intersection point of the two curves, and then the rightmost intersection point of those two curves. So once I find the x value of these two intersection points, I will have my limits of integration. So these 2 points are where those two functions are equivalent because they're sharing that same point. So in order to find my limits of integration, what I'm going to do is set these two functions equal to each other. So I can see in the graph where those two functions are equivalent. That would be those intersection points. Algebraically, I can find the value of those ordered pairs by setting my functions equal to each other. And I just need the x value. So I don't need the entire ordered pair of those 2 points, just the x value, so that I know what my closed interval is and what my limits of integration are. Okay, so let's solve this quadratic equation. So I want everything on one side set equal to 0 so that I can factor it or use the quadratic formula if I must. So I like for my x squared term to have a positive coefficient. So that means that to get that, I'm going to move the terms from the right to the left. So I'm going to move that minus x squared and the plus 5 to the left side of the equal sign so that I get a positive coefficient on my squared term. So that's going to give me a positive x squared. I still have the plus x and the minus 1. And when I move the 5, it becomes minus 5 on the left. And now it's set equal to 0. And I can go ahead and combine those two like terms, the two constants, and there's the quadratic equation that I want to factor. So factoring this, it factors into x plus 3, x minus 2. And when I solve for x, I get x is equal to negative 3, x is equal to 2, and those become my limits of integration when I set up my integral. So we're about ready to get that integral set up. So I'm going to draw my integral symbol, and I'm going to put my limits of integration. My limits of integration are negative 3 to 2. Remember that you always want the smaller value on the bottom, the larger value on top for your limits of integration. And now we have to create the integrand. So when you look back up here at that definition that I pointed out, remember the integrand is the difference between the two functions. Now, because subtraction is not commutative, it does matter what order I subtract those functions in. you want to look back at that drawing again to determine whether you're going to do the parabola minus the line or the line minus the parabola. And when you look at the drawing, you can determine this by looking at that shaded region in blue and figuring out which curve was on top of that shaded region and which curve is on the bottom of that shaded region. And you're always going to do the top curve minus the bottom curve. So when I look at this shaded region here, the piece, the boundary that's on top of that area is a piece of the parabola, which means that in my integrand, my parabola is going to go first. So I'm going to put minus x squared plus 5 first. And when I look back at the picture, on the bottom of the shaded region is a piece of the line. So in my integrand, I'm going to subtract the line, the linear function. So this is what my integrand should look like. And now I want to combine my like terms, get rid of the parentheses before I actually perform the integration. So I can distribute that -1 here, which would give me minus x plus 1. And then I can also combine my like terms. The +5 and the +1 can be combined together. So it gives me an integral from -3 to 2 of -x squared minus x plus 6, and then don't forget your notation, dx. So that's what I want to integrate. So now we're going to just perform the integration using our rules of integration and then evaluate that antiderivative from -3 to 2. So if I integrate first, I'm going to have coefficient over exponent plus 1 minus coefficient over exponent plus 1, and the integral of 6 is 6x. And then remember, this is a definite integral, so we don't have our plus c. All we want to do is indicate that we're going to evaluate this from -3 to 2. So remember to evaluate that, and I'm going to shoot up here, is that we're going to plug in for x our upper limit of integration minus, then we're going to plug in our lower limit of integration. So I'm going to start by replacing all of those x's with 2, and I'm going to use a bracket here. And I've got -1/3, 2 cubed, minus 1/2, 2 squared, plus 6 times 2. And I want to subtract from that same thing, only this time I'm plugging in my lower limit of integration, which is -3. So minus 1/2, -3 squared, and plus 6 times -3. And I'm running out of room. So now I want to do that evaluation. So that last term there looks a little ugly. Let me fix that a little bit so it's readable. So that should be a -3. Okay, so in the first set of brackets, I want to do all of this arithmetic, and you can just get on your calculator and plug all of that in. And when you do that, you get 22/3. I would recommend using fractions and not decimals because we want an exact value for this, and 22/3 doesn't have an exact decimal value. So just leave your answer as fractions. And then we've got minus, and in this set of brackets, I'm going to end up with -27/2. So minus minus becomes plus. So when I add those two fractions together, I get my overall area between those two curves as 125 divided by 6, or 125/6. It's hard to say. Okay, so there's 3 steps. First, draw a picture. Now in this one, I had the picture drawn for you, but I won't always have that picture drawn. You don't have to do an exact graph, but you do need to be able to draw it enough where you know what that shaded region looks like. The second step is to find your limits of integration by finding the intersection points. So set the two functions equal to each other. And then the third step is to create your integrand by looking at your picture and determining which function is on top of the shaded region minus which function is on the bottom of that shaded region. So let's take a look at an example where I do not have the picture drawn for you. So in this first one here, we've got a problem where we want to find the area of the region bounded by the curve y equals x squared plus 2x plus 3, so another parabola, and another line y equals 2x plus 4. So when you go to sketch the curve, you don't have to plot a bunch of points, you don't have to find the vertex of the parabola. What you really want to do is just sketch these two curves on top of one another in a way that you can see what that bounded region would look like. So I know that this first curve is a parabola that opens up. So I'm just going to sketch a parabola that opens up. And I know that this second one is a line with a positive slope. So on top of that parabola, draw a line with a positive slope. So that's enough for my picture, which means that the area that I'm trying to find is the area bounded by those two curves. So remember, you want a portion of each of the curves all around that shaded region. So I wouldn't shade up here because I don't have a top to it. That area would keep going on up forever and ever. So you want to make sure that you've got a boundary on every side of that shaded region. And a portion of that boundary is going to be the line, and a portion of that boundary will be the parabola. Okay, so we've got our picture drawn. So the next step is to find the limits of integration. So that means finding where these two functions intersect. So to do that, I'm going to set the two functions equal to each other and solve for x. So again, I have a quadratic equation that I want to get set equal to 0. So if I move the 2x and the 4 to the left, the 2x's will subtract out, and 3 minus 4 is -1. So I've got x squared minus 1 equals 0, which we know that gives us x equal to 1, x equal to -1. And if you need to factor that one more time, I'm sorry, I didn't mean to skip a step, but it will factor as the difference of two squares, x plus 1, x minus 1. We've just seen that so often that I assume we can get right to the answer. So there are my two limits of integration. So now I want to set up my integral. So my integral is going to go from the smaller of those values to the larger, so -1 to 1. And now I want to create my integrand. So again, this is where I go back to the picture. And when you look at that bounded region here, notice what's on top of that region is a piece of the line. So that means in my integrand, I'm going to put the function that describes that line first, the 2x plus 4, minus, on the bottom of that shaded region is a piece of the parabola. So I want to subtract from that the parabola and make sure that you put that parabolic function in parentheses so that you don't forget to distribute the negative when you combine your like terms in that integrand. So let me rewrite this integrand. So I'm going to take and distribute this minus sign through that set of parentheses. So that's going to give me minus x squared minus 2x minus 3. And if I combine my like terms, I'm going to scooch up here. I've got an integral from -1 to 1. And when I combine all that, I've got minus x squared. The 2x's subtract out, and I've got plus 1. There's my integrand with respect to x. So now I'm ready to integrate. So my antiderivative will be coefficient over exponent plus 1. And for my 1, remember that you want to multiply that by x, so I'd have 1x. And I want to evaluate that from -1 to 1. So I want to plug in my upper limit of integration first. So I'm going to have -1/3 1 cubed times 1 cubed plus 1 minus -1/3 times -1 cubed plus a -1. And just to save a little bit of time, if you do all of that arithmetic, you're going to end up with 2/3 plus 2/3. So you end up with an overall area of 4/3. So check my arithmetic. You know enough of seeing me in class to know I can make an arithmetic mistake as good as anyone else. So if you see an error, make sure you reach out and let me know. Okay, so now's a good time for you to pause the video and take a minute to try example number 3, and then come back and see if you got your answer correct. So in number 3, we want to find the area of the region bounded by, this time we've got 2 parabolas. We've got 2 quadratic equations or functions. So I want to first draw my picture. So the first curve is a parabola that opens up. So I'm going to draw that. And my second function is a parabola that opens down. So right on top of that parabola, I'm going to draw a parabola that opens down. And then this creates that region that we want to find the area for. So the region that has boundaries on all sides is this region here. That's what I want to find the area for. So I want to start by finding the limits of integration. I want to find those 2 intersection points, which means setting the 2 functions equal to each other. So x squared equals 18 minus x squared. So again, if I pull everything to the left, I'm going to have 2x squared minus 18 equals 0. And I can factor out a greatest common factor of 2. And then I can factor that as the difference of 2 squares. And that will give me my 2 limits of integration, -3 and +3. So I'm ready to set up my integral. My integral is going to go from the smallest intersection value of x and my larger, so -3 to 3. And now I want to figure out my integrand. So looking back again at that picture, I noticed that on top of that area is the piece of the parabola that opens down. That would be 18 minus x squared. And I want to subtract from that the bottom portion of that area, which is a piece of the parabola that opens up. So I want to subtract the x squared dx. So that's going to give me my integral from -3 to 3 of 18 minus 2x squared dx. So if I integrate that, I'm going to get 8x minus coefficient over exponent plus 1. And I want to evaluate that from -3 to 3. So plugging in the 3 first, everywhere I see an x, and I want to subtract from that. That's an ugly 3, let me fix that. Subtract from that what I get when I plug in a -3 everywhere I see an x. And now again, the arithmetic I've already kind of done on the side, and you end up then with an overall area of 72. So again, check my arithmetic. Okay, we've got one more example. This one's a little bit different than the ones that we've done before, so it's worth going through and finishing out the video because it is different than the previous two. Okay, now we start this problem the same way that we started the other problems, but let's take a look at what that drawing is going to look like. Now I'm going to go ahead and sketch in a little bit of X and Y axis here, just because I want to try to do my graph relatively accurate on this one, although I am going to, on this first function, y equal x cubed, sort of overemphasize the turn here. So we know that x cubed is the basic cubic function that looks like this. Well, that doesn't look very good, but you get the idea. So when I draw that in, I'm just making it worse. So my basic cubic function looks like that. So when I draw it in on these axes, I'm going to really overemphasize kind of that turn in there, just because I want you to see what happens when I put that line with the positive slope on top of it. So if I draw in a line with a positive slope on top of that x cubed, notice what happens. When I do that, the area that's bounded by the two curves is actually two separate areas. So I've got two areas that I need to compute and then add those two areas together in order to get the entire area that is bounded by these two curves. Now, let's say that when you drew that, you didn't overemphasize it like I did, and you didn't see that it had two areas. I'm going to show you in setting up the problem how you're going to know that there are two areas, even if your sketch didn't show two areas. So what we need to do, our next step always, is to find the intersection points of those functions. And this is kind of where you're going to find out, that's going to clue you into this isn't a traditional problem with a single bounded region. So what we do to find those limits of integration, we set those two functions equal to each other and solve for x. So I'm going to get it set equal to 0 so that I can factor it, and I can pull out a greatest common factor of x, leaving me x squared minus 9, and then that factors as the difference of two squares, x plus 3, x minus 3, giving me x equal to 0, x equal to negative 3, and x equal to 3. So here's your first hint that I've got two areas that are bounded by these two curves, and that's that I have three separate limits of integration. So the only way that I can get those in my integrals is to set up two separate integrals. So the first integral is going to go from the smallest value to the next value, so negative 3 to 0. And my second integral is going to pick right back up at that 0 and then go to the largest limit of integration, which is 3. And you can see that on the curve. So here would be my negative 3, there's my 0, and there would be my positive 3. So we're integrating from negative 3 to 0 to get that first area, and then integrating again from 0 to 3 to get that second area. And then we're just going to add those two together. Okay, for my integrand, now again, we have to be careful and look at each area and make sure that we get the integrand in the right order when we subtract. So if we look at that first area on the left, we see that on top of the area is the x cubed function. So for this one, x cubed is going to go first. And underneath that area is the line. So I'm going to have minus 9x dx. And then we're going to add that to the second area, which for the second area, the line is on top. So my 9x goes first, and the x cubed is on the bottom of that area, so we're going to subtract x cubed dx. Now, if I go ahead and integrate, I'm going to have coefficient over exponent plus 1 minus coefficient over exponent plus 1, and that is going to be evaluated from -3 to 0. And then we're going to add that to coefficient over exponent plus 1 minus coefficient over exponent plus 1, and that's going to be evaluated from 0 to 3. So if we go ahead and do the evaluation on the first set, we want to replace all of those x's with 0, which is nice because I'm just going to get 0, minus what I would get when I replaced all of those x's with -3. And then I'm going to add that to what I get over here when I evaluate. So I'm going to plug in my 3 everywhere I see an x, minus 0. And if I plug 0 everywhere I see an x, that just turns into 0. So when you do this arithmetic, you're going to get this minus sign, and then inside that bracket you get -81/4, plus over here in the bracket you get 81/4, and then minus 0 keeps it 81/4. So this is going to be positive 81/4 plus another 81/4 gives me a final value of 162/4. So there's my area. So in finding the limits of integration, if you end up with 3 limits of integration, that's your indicator that you're going to need to separate this into 2 integrals. And it might be your indicator then that when you're looking at the graph, that you do the graph a little bit more accurately than just a sketch of one curve over the other curve like we did in the previous examples, so that you can actually see what those 2 areas look like. Okay, if you have any questions either on the video or on the homework, make sure that you email me. And this was our last section, so the next couple of videos that you see coming are going to be to review for your exam, and then also to review for your final exam.